Very good morning. Welcome to the 6th week lecture of Applied Multivariate Statistical Modeling. In this week, we will discuss analysis of variance. Today, we introduce the topic analysis of variance. You will see conceptual model in terms of different hypotheses and the parameters, and we will discuss also the Bartlett test for test of equality of population variances. If you recall last week lecture, so you have seen there we have discussed about multivariate inferential statistics up to hypothesis testing and considering two populations. Today you will find something more. Let us see the next.
Today we will discuss analysis of variance. Popularly known as ANOVA. In last class, we have discussed about the difference between two population means, and in hypothesis testing, we have covered the equality of population means from univariate point of view, from multivariate point of view. So, if we just recapitulate this, what we will find out that one is number of population, then your number of variables, then hypothesis, then the techniques used. What technique is used? If you say number of population L, number of variable P, and hypothesis as usual, then the situation is single population L equal to 1. Suppose number of variable is also 1, P equal to 1. What we do in hypothesis testing? We do H0 mu equal to mu 0 and H1 mu not equal to mu 0. Generally we test this, and we use for the small sample case t test. We assume that population is normal. Now, L can be 1 and P can be more than 2 all case also, that is single population more than or equal to 2 variables, and your hypothesis will be again H0 mu equal to mu 0, here mu is a vector quantity, and H1 mu not equal to mu 0, and we have used Hotelling's t square for hypothesis testing, again for small sample case. Now, second issue we have discussed L equal to 2 population case. Under this also we have already discussed P equal to 1 case, and there our hypothesis was mu L equal to mu m, and alternative hypothesis we have framed as mu L not equal to mu m for at least one pair, and we have used t test. And for P greater than equal to 2 case, we have hypothesis like this, that mu L equal to mu m, here mu and L and mu m are vector quantity, and H1 mu L not equal to mu m for at least one pair, and we also used Hotelling's t square. Okay. So, this is what from hypothesis testing point of view we have already completed. What will happen when L is 3 or more? So, our discussion today for L greater than equal to 3 case where L stand for population, that is number of population. Okay. So, in this case we will first consider the univariate issue, that means we are interested in P equal to 1 case, and when we test equality of several population means for one response variable, the technique used is ANOVA, analysis of variance. So, that means what I said, that suppose your case is P equal to 1, that is univariate case, there are several groups or population which is definitely 3 or more. In that case the t test is not applicable. Simultaneously, if you want to test the difference, you require to use a special technique known as analysis of variance. So, today we will see in terms of ANOVA. For ANOVA, these are the contents: conceptual model, assumptions, estimation of parameters, model adequacy tests, interpretation of results, followed by references. What is this conceptual model? I will be describing with an example. You see this slide here, we have 3 processes A, B and C. These 3 processes are producing, let steel washers. So, our product is steel washers. Steel washer is the product, which can be in 2 dimensional figure, we can see like this. Suppose this is the case, and then this part, or other way, this inner circle part, if we consider, this is ID, inner diameter, and if you consider the outer circle, this will be OD, which is outer diameter. Let both are measured in millimeter. Millimeter is the case. Here these values are in millimeter for outer diameter. The problem is that you are producing through 3 different processes, but you are producing same thing, that is steel washer, and outer diameter is the quality variable and which is specified by the customers. Okay. Now, as a manufacturer of these steel washers, what you require to know? You require to know that whether all the processes are producing at the same level from quality point of view, same level or not. And the manufacturer is interested to test the differences in means of outer diameter for the 3 processes. So, our objective here is, are there mean differences in outer diameter of the washers produced by any 2 of the 3 processes. Okay. Under such situation, the most widely used graphical plot is box plot. Okay. Now, see what is box plot. This figure shows box plot. This box plot is for process A, this is for process B and process C. In the box plot, there is one box and 2 whiskers. This one is box, the upper portion, this line is right whiskers and this is the left whisker. This box is determined by interquartile range IQR, and the horizontal middle line here, this is the median position from the data, and the circle plus 1, that is the mean position. Okay. So, if we see the three boxes here for process B and process A as well as process C, what we will find out that the box hardly differs in terms of variability except process C, but it is to be proven that whether this variability is different from A or B or not, but apparently it is different. Okay. But if you see the mean point, the circle plus point, this one is quite different. Apparently it shows that there is mean difference. You see, this is the mean point for process A, this is mean point for process B, this one is mean point for process C, and if I see the value, it is 20 point something, this one is around 18 and this one is again 20 point something. So, even if there is no difference between maybe process A means versus process C means, but there is chance that both process A and C means are different from process B, which is basically from the graphical plot it resembles like this. But what you want a quantitative explanation of this, and if we are able to do this, then we are able to answer this question, are there mean differences in OD of the washers produced by this. Then we will use, I told that ANOVA. ANOVA uses two hypotheses, one is null hypothesis and alternative hypothesis. What null hypothesis says? Null hypothesis says that there is no mean difference. As we have taken three processes A, B and C, so we are saying that process A mean as mu1, process B as mu2 and process C as mu3, and there is no difference means mu1 equal to mu2 equal to mu3. And our alternative hypothesis is at least one of the pairs, that means either mu1 mu2 pair or mu1 mu3 pair or mu2 mu3 pair is different, that means are different. So, pictorially the left hand side figure is your null hypothesis and here the right hand side is your alternative hypothesis. If your situation is as the left hand side figure, you see what happened here, there is one parameter mu, please see the left hand side, this is mu here, this mu is the grand mean, grand mean. So, there is one parameter called mu which is known as grand mean. By grand mean what do we mean? By grand mean we mean that you have three processes here in this case. So, you have produced several items, you have measured the outer diameter in this case, irrespective of the process you take everything as a whole and compute the mean. Okay. This is what is grand mean, the totality. For example, in this case we have seen that we will collect certain amount of data and we have collected 10 data points, sample size is 10 for process A, process B and process C, 10 each. So, what will happen ultimately, total data point if I say n, that is 30 and you are considering every data points, all sum. So, sum of all the data points divided by 30, that is your grand mean. If you collect 30 data points, 10 from each of the processes, that will become your grand mean. Okay. Now, there is another mean which is known as process mean, or in this case we will say the population mean, because we have assumed that each of the processes are different as if each of the processes are representing a population. Process A is one population, process B is another, process C is the other one. Mu 1 is the mean of process A, mu 2 is the mean of process B, and mu 3 is the mean of process C. When null hypothesis is true, that means mu 1 equal to mu 2 equal to mu 3, then it will be equal to mu. Okay, because we are you are collecting here 10 samples from each of the population, and when null hypothesis is true, what will happen? You compute the process A mean, process B mean, process C mean, you will be also the grand mean, you will be finding that they are equal, because it is obvious. Because what is the group mean calculation? Do you know that? I think all of you know N1 F1 plus N2 F2 plus N3 F3 by N1 plus N2 plus N3, that is the group mean. Okay. If you calculate group mean, this is the formula, where for the first case frequency is F1, second case frequency is this is basically F1. Okay. N1 F1, N2 F2, N3 F3, and N1 is the number of cases from the, that is the, I think we have to use mu here, N1 into mu plus N2 F1 is, it is basically mu 1 mu 2, that will be better. So, I will write like this, N1 mu 1 plus N2 mu 2 plus N3 mu 3 by N1 plus N2 plus N3. Okay. So, this is the general expression, we will not consider, we will consider this one here. So, if mu 1, mu 2 and mu 3 are same, then what is happening here? Then it is mu N1 plus N2 plus N3 by N1 plus N2 plus N3. This will be cancelled out, this is mu equal to mu. So, grand mean will be like this. Now, let us see that what are the other parameters available here. You see the left hand side again, there is another parameter which is epsilon IL, this one. This is the error quantity. Error in the sense, if you take any observation xi1 for the first process, from the first process, then if we consider that mu 1 equal to mu, then mu 1 will come here, the difference between the two, that is the observed value minus the mean value, that is epsilon IL. Later on we will see this is basically error quantity. So, similarly for mu 2 also epsilon I2, for mu 3, that is process C case also epsilon I3 you are getting. Now, come to the right hand side. In the right hand side, what is happening, what this figure resembles that the mu 1, mu 2 and mu 3 are not same. So, they are not coinciding with mu, and as a result what will happen, you will be getting one more parameter here, that is known as tau. You see, this is tau, this one is also tau, this is tau. So, tau 1 is this value. What is this? This is the process mean minus grand mean, and tau 2 is again the process mean minus grand mean for process B, tau 3 is process mean minus grand mean for process C. So, one more parameter is coming into picture. So, what we will do, using all those things, we will redefine the ANOVA model, and that is that any observation can be partitioned into three parts, that is XIL is the observation, that is the ith observation on the nth population to be collected, mu is the grand mean, tau L is the population effect, and epsilon IL is the error term, which is not captured either through grand mean or tau L, or combiningly it is not captured basically. Okay. So, and what is tau L? Tau L is the population effect. So, nth population effect is tau L, which is also known as treatment effect. So, this is mu L minus mu, that means the mean of nth population minus grand mean, and other one epsilon IL, that is the error part, is calculated like this. Here we, this right hand side, there are two conditions given, one is L equal to 1 to L tau I L equal to 0 for equal sample size case, means when you collect sample same sample size sample from the three populations or L population, what will happen here, you will find out that their effect will be, total effect will be 0. When one is more than the other, some cases some are more than the mean grand mean, some are less than the grand mean, but the total effect will be 0. And if you go for unequal sample size, then your formula will be like this, L equal to 1 to L N L tau L equal to 0. Okay. I think let me repeat this. What we are saying in ANOVA case, we are saying that you have number of observations in this case, here it is number of population. Okay. So, you may find out that several population and also here will be several observations. Suppose I am saying that one observation is XIL, that is the general observation, that means ith observation on the Lth population, this is my Lth population. What we are saying further that XIL, it can be decomposed as grand mean plus your population effect plus some error quantity. How do you get it? We will get it like by this manner, XIL equal to, I can write mu plus, let me write like this, mu L minus mu. So, mu cancelled out, mu L is there, but left hand side is XIL. So, XIL minus mu L. See, mu and mu will be cancelled out, mu L will be cancelled out. So, XIL equal to XIL. So, this is what is known as partitioning observation into three components here. One is grand mean, other one is the tau L, that is the population effect, and this one is epsilon I L. So, you are partitioning the observation values into three component here, and each component is a parameter of ANOVA. That is, from conceptual point of view, that there are three parameters, one is mu, another one is tau L and error component. Three things are there. Okay. If this is the case, then your hypothesis can be changed to H0, that is mu L tau L equal to mu L minus mu equal to 0, and H1 tau L not equal to 0 for at least 1 L. For at least 1 L. Like other multivariate models, ANOVA comes under univariate model. Like other multivariate model or like any model, any statistical model, that ANOVA also requires certain assumptions to be satisfied. These assumptions are populations variances are equal. So, you are sampling from L populations, the population variances must be equal. That means, what I mean to say, sigma 1 square equal to sigma 2 square equal to sigma L square. Okay, this to be satisfied. This is our first assumption, assumption 1. Assumption 2 is errors are normally distributed. What is this error? You have seen earlier that we have said that epsilon I L equal to x I L minus mu L. If you estimate this, this will be like this. So, this error quantity is normally distributed. Errors are IID, mean independent and identically distributed. If I say error 1 is normally distributed, then error n also normally distributed, that is identically distributed. Independent means there is no correlation between the errors. Okay. So, normal distribution as well as IID condition, those things you know, and how to test the normality we have also discussed earlier in some lectures. Now, I will first explain how to test the equality of population variances. If the this one is not satisfied, this assumption 1, that is equality of population variances, is not satisfied, what will happen then? You cannot use the traditional ANOVA. Okay, it is there, some other methods are there, but you have to go for different way of doing things, but here this assumption is vital for us. So, for equality of population variances, you will use Bartlett test. Bartlett test. Okay. Now, see the format what we have written here: hypothesis, statistic and decision, and that you have seen earlier also. Okay. Now, what is our hypothesis? That there is no differences in the population variances, and alternative hypothesis is at least one pair of variances are different. Okay. Now, here Bartlett proposed one statistic which is 2.3026 Q by C. This is a statistic where Q is n minus L log 10 SP square minus L equal to 1 to L NL minus 1 log 10 SL square. I hope you can recollect what is SP square and what is SL square. Okay. This is pooled variance and this one is individual population variance. So, you require to compute first L1, S1, S2 square, S1 3 square, S4 square, like the all individual population variance values. Then also you require to compute the pooled one. This pooled one is given in this equation, SP square equal to L equal to 1 to capital L NL minus 1 SL square by N minus L. I think that you have already seen in last class. What we are saying that SP square, this is N1 minus 1 S1, N2 minus 1 S2, like this, NL minus 1 SL divided by N1 plus N2 up to NL minus the how many populations are there, that is L. So, this quantity is nothing but NL minus 1 SL, L equal to 1 to L divided by sum total of NL minus L, where L equal to 1 to capital L. So, this is your SP square you have developed earlier also. If you know this, then you are in a position to calculate Q. What is capital N here? Which one? N minus L minus L. This capital N is nothing but this one. Capital N is L equal to 1 to capital L small n L. That means the total sample size from all the population. Although it is total sample size is not that meaningful, mean from every population you collected certain sample of size, some sizes, and that totality we are talking about. Then you have to compute key C. C is 1 plus 1 by 3 L minus 1, L equal to 1 to L, NL minus 1 inverse minus N minus L inverse. This is your C value. Okay. So, please go through this C. There are basically C is another quantity which is basically L and N values are depicting this C, and this C will be used as the divisor. So, then chi square is 2.3026 Q by C. So, given data set you have to calculate Q, you have to calculate C, then you find out the chi square value. Chi square is 2.3026 Q by C, and what does it mean when you say chi square? Because this quantity follows chi square distribution, and what will be the degrees of freedom, that you see it is clearly written here in the decision case, that reject H0 when the chi square computed is greater than chi square L minus 1 for a particular alpha value. So, what do we mean then? That 2.3026 Q by C follows chi square distribution with L minus 1 degrees of freedom. Correct. I think the similar thing you have seen earlier also, we are repeating. See the same problem. So, we have 30 observations, 10 from each of the processes, and what we have done here, we have calculated the variance for the first process, that is 1.51, variance for the second process, that is 1.43, variance for the third process, that is 0.93, and then you have computed chi square by that is this one is chi square. So, you have computed first pooled variance, then Q, then C, then chi square which is 0.25. Now, we all know that chi square with 2 degrees of freedom and alpha equal to 0.05, this value is 5.99. We have seen this one earlier also. Now, the computed value is less than the tabulated value. So, what will be your decision? You will accept null hypothesis or reject null hypothesis? Accept null hypothesis. You fail to reject null hypothesis. So, the same principle, this is my chi square, suppose this is your chi square distribution, your alpha tabulated value here, this is 5.99, but your value is how much? 0.25, it is very close to 0. So, what does it signify? It signifies that there is no population variance differences, all the population variances are equal, same. So, we are fit for ANOVA case. Okay.